In this lecture, we're going to introduce another type of constraint called a subtour elimination constraint. Before we do that, though, we need to introduce a new problem. We've talked about the traveling salesman problem before. Now we're going to introduce a version of it called the prize collecting traveling salesman problem. I'm still going to refer to this as just the traveling salesman problem, though. In the traveling salesman problem, this version of it, we're given as input a graph, a distance on every edge, and a start node S. This is the same input as the traveling salesman problem. The difference now is that we're also going to be given a reward for every vertex. This reward is an amount that we're going to collect if our traveling salesman actually visits this node. Our objective is to find S star, an optimal set of nodes, so that our start node is in this optimal set, and we develop a tour that visits every node inside of this set exactly once. Our objective is to find a set so that we maximize our reward when we take into account the total distance that we need to travel to visit all of the vertices inside of our set S star. We can see how the traveling salesman problem works with our little example over here. Here we're given a set of nodes, and there's 5 of them. We're given our start node S. Our optimal solution is to pick only 2 of these nodes, circled in S star, and to have a tour that visits each of these nodes exactly once. Note that in this tour, every vertex is adjacent to exactly 2 edges inside of the tour. We can write the traveling salesman problem, or the prize collecting version of it, as an integer program. The objective value of this integer program is to maximize our reward when we also include the cost of visiting all the nodes that we'd like to. The integer program has 2 sets of variables to do this. The first is the set x. The set xv indicates which of the vertices that we're going to visit. The set of variables y indicate which edges we're going to include in our tour. Note that after we pick our set of vertices, we still have a decision to make, the optimal tour to travel through them. The constraints for our integer program are first, that if we pick a node to be in our set S star, that the number of edges that are adjacent to it is equal to 2. This constraint encapsulates that. We've introduced a notation that we've seen before, delta v. Delta v is the set of all edges that are adjacent to a vertex v. And this constraint says that there's 2 edges adjacent to a vertex v if xv is equal to 1. The second constraint just tells us that the set S star has to include our initial starting node S. The third set of constraints are the powerful set of constraints. They're the so-called subtour elimination constraints. We're going to deal with them on the next slide. For now, though, we'll get an idea of what these constraints are saying. In effect, it's telling us that if we look at some set of nodes, S, any set, not necessarily S star, and we take away exactly one of the vertices out of S, that the number of edges has to be exactly equal to the number of vertices inside of the set S with one node removed. Here we've introduced new notation E of S. E of S is the set of edges that are completely contained inside of S. That is, both endpoints have to be inside of S. We'll examine the subtour elimination constraint in the next slide. To get an idea of the subtour elimination constraint, it's best to consider a particular example. Here we have a small example with 5 nodes, where we've chosen a set S star that includes the nodes 1, 2, and S. Our subtour elimination constraint is effectively telling us that the number of edges completely contained in our set S is going to be 1 less than the number of nodes that is required to visit inside of this set. Note that the subtour elimination constraint takes only sets S that don't include our initial starting node S, and that we eliminate exactly 1 node inside of S to write each one of these constraints. In effect, the number of constraints is exponential because there's 1 for every subset, but on top of that, for every subset, we also remove every element inside of S. To see why this constraint is true, first we consider the optimal set S star. Because S star includes the node S, we remove the node S to get the set S naught. If we write the constraint for S naught, we can analyze both sides of this inequality. Let's suppose that we remove node 1. If that's the case, then the sum of the xv's is exactly equal to 1. That is, there's only one node, node 2, that we have to visit. Also note that the number of edges completely contained inside of S naught is 1. It's only the edge 1, 2. And so this constraint is met with equality. This is the main intuition behind this constraint, that the number of edges completely contained in the optimal set is going to be 1 less than the number of nodes that have to be visited inside of this set. To show that this is a valid constraint, though, we have to show that for any set S that this constraint is actually satisfied. To do that, we're going to consider another set. In this case, we're going to consider the set S1. S1 isn't associated with the optimal set, but it includes all of the nodes that we've chosen, 1 and 2, and an additional node 3. If we look at S1 and we remove node 2, then the sum of the xv's is equal to 1. If we look at the set of edges that's completely contained inside of this set S1, then we note that it's also equal to 1, and so this constraint is satisfied. In this case, it's met with equality. This is a general trend. We removed a node that's part of our optimal solution, and by doing so, we only need 1 minus, or the number of nodes minus this 1 number of edges to visit all these nodes. However, if we look at this same set S1, and we remove one of the nodes, in this case 3, that's not associated with our optimal solution, then we see that the number of edges that are required to the number of edges is not equal to the number of nodes minus 1. In this case, the number of edges that's completely contained inside of S1 stays the same, namely 1, but now the number of nodes that are in our optimal solution is 2. In this case, because we removed one of the non-optimal nodes. Finally, if we consider some set, let's say S2, that includes none of the optimal nodes, then both sides of this inequality are going to be equal to 0, and so it will be met with equality. The hardest part of showing that this equality is going to be valid for every set S is effectively this green portion. It's going to be associated with sets S that cross across, that include both optimal, that is xv equal to 1, and non-optimal, xv equal to 0 nodes. In this case, we can effectively convince ourselves that this constraint is going to be satisfied, but it might take a little bit more work than what I've shown here. The subtour elimination constraints are powerful. By including the subtour elimination constraints, we can exactly characterize the traveling salesman problem, or in this case, the prize collecting version of it. Unfortunately, in this case, the number of constraints is exponential. And so in order to even define the problem as an integer program, we have an exponential number of constraints. What we'd like to do then is solve the separation problem. In this case, the separation problem isn't just to make our formulation more powerful, but to make our formulation accurate to begin with. If we have a separation algorithm, our idea is going to stay the same though. We'll solve the linear program and continuously introduce subtour elimination constraints as they're needed.